So essentially, last lecture where we stopped was we wanted to get the coupled differential equations that are given in foot, specifically equation 7.9 and 7.10. Um, those equations are coupled differential equations which come when we substitute, which result when you substitute the Hamiltonian, interaction Hamiltonian, and the initial Hamiltonian of the atom, which is yeah, which is H0, and H0 is the atom's Hamiltonian, their Hamiltonian, and the Hi is the interaction Hamiltonian. So H is the total Hamiltonian of the system. Interaction Hamiltonian is interaction of light and atom, as always for us in this course, and this is just an atom. So later, when we will consider the quantized version of the light, we will also consider one more term, which will be then for the light. But right now, we are not considering the Hamiltonian for the light because that will be a harmonic oscillator Hamiltonian. But right now, we just have two terms, which because we are treating light as classical and atom as quantum mechanical. That's why we have atom and light atom interaction Hamiltonian. So we have two terms in the Hamiltonian, and the complete solution, the total wave function in space and time, is we have constructed this. We have assumed that it will have this form, and that is given as C1, the coefficient which is time dependent. C1 and C2 are time dependent coefficients because the time evolution of the system. Initially, you have some population which is C1 square and C2 square in first level and second level. So we are always in this course we are always talking about two-level systems, right? So in two-level systems, we will have C1 square coefficient, which gives the population in the first level, ground state, and C2 square coefficient, which gives you population in the excited state. So those populations now themselves, those coefficients themselves become time dependent because as you are imparting a perturbation on the system, which is like an external force or external radiation, because of that external radiation or force, your population levels change. So your energy levels get occupied, excited energy levels get occupied, and so your populations change. So if you start with all the population in the ground state, some of the population gets excited in the excited state. That's why the coefficients themselves get time dependent. So the total wave function for this total Hamiltonian becomes C1t, is given as this expression, and this expression has three terms basically. One is one is the phase factor, second is the time dependent coefficients, and third is the energy eigengets at the start. So which was the energy eigenstates of the initial Hamiltonian H0. So 1 and 2, those gets are the energy eigenvectors of the initial Hamiltonian. So if we consider that as psi, then what we want to do is we want to solve Schrodinger's time-dependent equation, right? Always to get the time evolution of the system. Why is that the case? Because the time evolution is directly dependent on how much energy you possess at a specific amount of time, specific moment of time. So whatever energy you possess, that will determine what will be the dynamics of the system or how will the system evolve as a function of time. So that's why we always equate it with the Hamiltonian, and that's why Hamiltonian decides how your system will propagate in time. And that's why the Schrodinger's time-dependent equation, that's why this is such a powerful equation that I h bar d psi by dt is equal to h psi. So now what we will do is we will take each side of this equation and then solve it exactly. So if we substitute psi, so if you consider equation 1, what we have done here is equation 1 is substituted in the left-hand side of this equation. And that gives you this. So this bracket essentially is substituted here. So if you take a time derivative, a partial time derivative of this psi of t, psi of space, it's a function of space and time again, but you are only derivating with respect to time. That's why there is a partial derivative. So that's why if you take a partial derivative with respect to time of this psi, then what you get is there are two terms here which are time dependent. So that's why you will apply, of course, a chain rule, and then that, and actually the energy eigengets, which is like 1 and 2, which are the eigenfunctions of the initial Hamiltonian, they are not at all time dependent. So they will just come outside, and you won't get any time derivative term because of those. So those are just constants for this derivation. Um, so what you get is IH bar C1 dot. What C1 dot represents is C1 dot is basically just the time derivative of the first coefficient. So C2 dot is similarly just the time derivative of the second coefficient, because the coefficients themselves are time dependent now, and we don't know the function of time. So we'll just keep it as uh, in this keep it in this form. So because of chain rule, we get two terms when we derivate the first term with respect to t, with respect to time. So first term is given like this, and the second term is given like this, because after the time derivative, the minus I omega 1 comes down. So these are the two terms that you get from the first term, and the other two terms similarly for the second term. So that's why starting from two terms, if we derivate them with respect to time, we get the four complete terms. So now, if we multiply I inside the bracket, and we also now want to club the other two terms, but we will do that later. So if we just multiply by that, then we want, so here from this step to this step, I am going to send this lecture note as well, so you can follow it later, uh, like go through it very slowly or derive it by yourself, and then compare it to this. So the reason why I'm going relatively quickly with this is because last time I think we discussed the same, but this time I have just written down the steps already, so it helps me get through it much quicker. So if we multiply this inside the bracket, then we get this term. And basically what I have done here, I have substituted E1 and E2 as where E1 is equal to h bar omega 1 and E2 is equal to h bar omega 2, because those are basically the energy levels. So omega 1 is the frequency, and omega 2 is also the frequency of the first and second energy level. And if you multiply by h bar, so like we talked about in one of the lectures, that whenever you have h bar, there has to be angular frequency alongside it for it to make sense energetically, for it to make sense dimension wise. So h bar times the angular frequency gives you energy units, and also h times the uh, natural frequency gives you the energy units. So if there is a h, there has to be a nu alongside it, and omega and nu are related by 2 pi factor, or omega and f are related by 2 pi factor. So f is the normal frequency and omega is the angular frequency. So here we are talking about angular frequency. That's why there is an h bar in the story. If we were talking about the normal frequency, there would have been just h, and there is no factor of 2 pi there. So you have to always remember that. So now if we have this expression, which came directly by just time taking a time derivative of the left hand side of the Schrodinger's time dependent equation, then if we pre-multiply by the first energy eigenket of the system, then what we get is the following. Uh, Now, in these four terms, I have cancelled some of the terms. I will explain why. But essentially, what we are going to do is we are going to pre-multiply by the first energy eigenket to both sides of this equation, Schrodinger's equation, and then we are going to equate the same coefficients. We are going to equate whatever remains. So if we do that, then we get this term. So we get four terms because if we pre-multiply by first energy eigenkette, we will get 1, 1, 1, 2, 2, 1, and 2, 2 whenever we are doing a matrix. But here we are only pre-multiplying by energy eigenkette 1. So what we will get is 1, 1, 1, 2, 1, 1, and 1, 2. So this is basically taking a matrix element, because whenever you multiply this with this and you have any operator inside, you are basically taking an expectation value if these two are the same. If let's say 1 and 2, if 1 and 2 are the same, then you are taking expectation value. If 1 and 2 are not the same, then you are taking a transition matrix element. So, but basically, this answer gives you a scalar. So this is a because this is a matrix element, this will be a scalar. So you need to remember this, that this gives you a scalar, and last time as we talked about, this multiplication gives you a matrix, which is a operator. So when we are taking transition matrix elements, of course, it's a scalar. So we are going to get scalars from this expression, and you can notice that the transition matrix element is basically telling us that this is our operator, and we are operating this operator on the first energy eigenkette. So we'll get something, and then that is what we are going to multiply with the first energy eigenbra. So this bracket basically gives you the transition matrix element, and whenever you will get that, what does it physically mean? So when you get such transition matrix element, what you're saying essentially is if you want to go from the first energy level to the second energy level, you want the transition matrix element of. So what does this mean physically is whenever you're talking about this expression here, you're operating your operator on the second energy eigenkette, and then you are multiplying with pre-multiplying with the first energy eigenbra, which means basically that the operator takes you from the second state to the first state. So this is basically telling you that how much what's the coefficient for going from the second excited state, sorry, from the second level to the first level. If it's the other way around, then if this is 2 and this is 1, then essentially what you're saying is you want to go from energy level 1 to energy level 2, and the operator takes you from energy level 1 to energy level 2. So it depending on whichever energy eigenkette the operator operates on the first, that this transition matrix element basically gives you what is the probability coefficient, what the coefficient for because coefficient square is probability. So what's the coefficient for going in the direction of from the first uh, level to the second level, or from the second level to the first level. So that's why whenever we are talking about going from one energy level to that energy level itself, it doesn't physically make a lot of sense. Um, but whenever we are talking about going from second energy level to the first energy level, or first to the second, then it makes sense to talk about different rates, because if you're going if you're going from the same energy level to the and coming back to the same energy level, that basically essentially you are not making any transition. You are staying where you are, and that doesn't make sense physically. That why do we even need to talk about that? So that's why it's like some of the terms here we can just cancel out by considering that they don't make sense, or that they are not physically like in the real world they are not interesting terms. So whenever we are talking about transition matrix elements, we always talk about going from one energy level to another energy level, or coming from another energy level to the first energy level. So actually, if you see, so when we pre-multiply the left-hand side of the Schrödinger's equation by first energy eigenkette, you can see that in the middle, whatever operator is there, that operator doesn't have any spatial term actually. So if it doesn't have any spatial term, like we talked about earlier, the energy eigenkettes actually are time independent. So if it is time independent, what we are going to get is, so this will just come out, and then if this comes out, then you'll get a pre and post multiplication of first energy eigenkette, and because you know that these are normalized, you already know that this is equal to 1, and similarly this is equal to 1, because all the energy eigenkettes are orthonormal, so they are orthogonal to each other and they are normalized. This is already known to us. So because these two conditions hold true for all the energy eigengets for any quantum system, that's why we can directly say that in the first term, we will get just a scalar factor. So, and why we are not considering the second term is because uh, we can, this will go to zero. Yeah, this will go to zero because they are orthogonal to each other. So you can see that if this comes outside, if this term comes outside of the transition matrix element, then basically essentially what you are doing is this operation, and this operation actually gives you zero. So that's why this second term of this expression goes to zero. Then third and fourth terms still remain, but we'll see that the right hand side exactly has the same terms. That's why we can cancel them out when we compare it to the right hand side. That's why I have cancelled it. But for now, you can consider only the second term has vanished. So first term is there, third term is there, and the fourth term is there whenever we are considering the expression for pre-multiplication of the first energy eigenvalue with the left-hand side of the Schrödinger's equation. So if we do that, um, then if we again do the operation, if we again do the same operation, but now consider the Hamiltonian operating on psi, then the Hamiltonian operating on psi actually gives us, uh, because H naught operating on psi 1 gives you E1 psi 1. That's why we get this E1. And similarly, we get E2. And we know that the interaction Hamiltonian has the form where interaction Hamiltonian is given by, so I am going rapidly because we already talked about this. So the interaction Hamiltonian was light atom interaction Hamiltonian, and where this is light and this is the dipole part. So if we consider this Hamiltonian operating on psi, then we will get these following terms. And then when we consider these following terms, uh, we can we can see that the first two terms, when H naught actually operates on psi, you get the exact same terms that you had in the third and fourth term of the left hand side. So this is the left hand side and this is the right hand side. So you can see that this term right here is exactly same as this term, and this term right here is exactly same as this term. That's why from the left hand side, right hand side, if both terms are equal, I have cancelled them out. So we can cancel these terms, and then we can cancel out one other term that comes in the right hand side because it is not physical. So since now there is a spatial part inside this bracket, that's why we cannot take it outside because the energy eigenvalues depend on the spatial part. So you have to operate then ER on the first energy eigenvalue. So basically this, since we are using Dirac's bracket notation, that's why we have written it like this. But I think foot gives you also the expression in terms of integral. So you have to, if you want to understand in terms of just normal algebra, which is in terms of integration, then you can consider that we are multiplying by psi1 and we are taking an integral. So this is the exact same in Dirac notation. So that's why we are using, because Dirac notation gives you much simplified and much cleaner picture. That's why we are using that notation, but you can use always the integral notation as well. So when we consider that, then if we see this term, then this term actually gives us a non-physical process, because if you are going from state one to state one itself, basically you are coming back to the same state, then any operator operating on that doesn't make sense. That's why even if this term comes in the mathematics, we can ignore that term because that is a non-physical term. So we don't need to consider the term where we are going from one state and coming back to the same state. That's why I have cancelled this term in the name of non-physical uh, meaning. So that's why whenever you operate the interaction Hamiltonian on the psi, you get two terms, and one of them you can already eliminate because you can say that if you want to go from one state to another state, then and only then this operation is valid. any operator is valid. That's why you get only one term from this. And the first two terms, like I said, are exactly same as the left-hand side terms. That's why they cancel out. So after all, so it's little chaotic to see here, but after all, after solving basically the left-hand side and right-hand side of the equation, if we compare them, then we get like a very simple expression where we get h bar and this expression, where this expression will simplify because these two will cancel out each other, and then we'll get just the simple I C1 dot. So C1 dot is the time derivative of C1 coefficient, and we can equate that to the right hand side, which is basically, so this giant term here, we can represent that as the Rabi frequency. So omega here is this expression, which basically gives you the frequency to go from one state to another state. So this gives you basically the coupling strength. So this is because if you consider E naught, then this electric field actually comes from the light itself, and the R actually comes from the atom. So the atom's dipole, so you can consider this as a dipole moment. So the atom's dipole moment, if it is high, then the coupling between the first and the second excited state, first and the second state of our two-level system will be high. And if we are incidenting a laser which is again of high intensity, then the high intensity laser will have high electric field as well. So the electric field strength, if it goes up, that also takes the interaction between first and the second state to a higher magnitude. So that's why you can quantify the interaction between the first, you can quantify this transition going from the first level to the second level, or you can quantify the interaction between the levels by a quantity which is called as Rabi frequency. So that's why this is, which is like an interaction strength. So that's why this is called as Rabi frequency, which gives you the coupling strength between level 2 and 1. So because we have just a two-level system, there is a coupling between those, and that coupling is given by this expression. And this expression basically is, if you have a dipole in a changing electric field, then the energy of that dipole, if you take an expectation value, but when the two energy eigengets are not the same, we don't say it's an expectation value. What we say is a transition matrix element. So you take the transition matrix element and divide it by h bar. That gives you basically the coupling strength. So that's why after simplification by again comparing the left and right hand side of the Schrodinger's time dependent equation, what we get is I C1 dot is equal to omega, which is capital omega, which is the Rabi frequency, times C2 times the cos omega t, and there is a phase factor e to the power minus I omega t. So this is, if you see carefully here, this omega naught is, so omega naught is the resonance frequency, and omega is the applied frequency of the laser. So omega is the external perturbation that we have applied, and omega naught is the resonance frequency, and the resonance frequency can also be given as the difference between the two energy levels, which is the difference between the second state and the first state. So we can also say that omega is just difference between the two frequencies. So which is the resonant frequency. So now we can compare that whatever frequency we have applied on the system. So if we have a two-level system and we are applying a laser on it, then we can talk about whether we are applying the frequency exactly same as the resonance frequency of the system. Because once we define our two-level system, we already know what is the frequency of the individual levels. Because we already considered that the two-level system that we have, we already know the energy levels of that system. And if we know the energy levels, we can find out the frequencies as well, because we just have to divide by h bar. So if we know both the frequencies of both the levels, then the difference between those frequencies gives us the resonance frequency. So once we know the resonance frequency of our system, then when we are applying a perturbation using a laser or using a light source, what we can do is we can either be at the same frequency as the resonant frequency, or we can be away from the resonant frequency. So there are two cases here we can consider where whether we are on resonance when we are driving the system, or we are off resonance when we are driving the system. And we are going to talk about both those scenarios. But this is the expression that we get. So this is like the coupled differential equation that in the last lecture we wanted to derive, but I didn't derive explicitly. But this lecture, I think, if you go through these notes, you should be able to, because this gives you all the steps, and that's how we reach the coupled differential equations, where now these two expressions are what we get when we solve everything. So this is what we get when we solve, and similarly, if you pre-multiply instead of the first energy eigenket, if you pre-multiply by second energy eigenket and go to the time dependent equation, then you get the following. So that's why you get these two expressions when you solve the Schrodinger's time dependent equation. And these two are coupled equation. What do you mean by coupled equation is on the left hand side there is C1, and on the right hand side there is the C2. And the time derivative of C1 is depends on the C2, and time derivative of C2 depends on the C1 coefficient. So that's why you have two coefficients which are unknown. So two unknowns which are coupled to each other. That's why these two are coupled first order differential equations, because the time derivative is in the first order. So, and it has both frequencies, which is one is applied frequency and one is the resonant frequency of the atom itself. And omega is the coupling strength, and T is time. So I hope these two expressions are clear. So these are the same expressions from the Foot book. This is equation, I think 7.9 and 7.10 in Foot. So you can see we have talked about the C1 coefficient. So here, remember that the coefficients are time dependent. So C1 coefficient square gives you the population in the first level, and C2 coefficient square gives you the population in the second level. Now, since they are time dependent now, the time derivatives are proportional on the coefficient itself, but they are cross coupled. So that's why these are coupled differential equations. So C1's time derivative depends on C2, and C2's time derivative depends on C1. Uh, and I hope all the quantities that are mentioned in this expression or in this equation are clear, that omega is the applied frequency of the laser and omega naught is the resonant frequency of the atom itself, because we are considered two-level system. So the energy difference between these two levels is omega naught. And capital omega here gives you the coupling strength, which is given by this expression. So the coupling between the first and the second excited state. Why is that coupling even existent? Because this will be zero. This coupling will be zero if we have not applied any external field. So the first and the second level is not going to interact, or any transition is not going to happen from the first level to the second level or second to the first level if we have not applied any electric field, or even if the atom doesn't have any dipole moment. So because this is a dipole interaction, that's why, because of the dipole interaction, this transition is happening, and that's why capital omega is non-zero. So these are the two expressions which are the coupled differential equations for our system. So our system was a two-level system, which is an atom is interacting with a light, where the light is considered as a classical electric wave, which is a changing electric wave. So till now, actually, everything that we have done has been exact. Like mathematically, we have not considered any approximations. We have not done any approximations in the derivation till now. So everything here has been exact. So there were no approximations, but from now on, we are going to deal with two different approximations in this derivation. First is the dipole approximation, and the second is rotating wave approximation. So I hope it is clear how we got to this point. And since we are at this point, we will now discuss about how to solve these coupled differential equations. Since these are two single order coupled differential equations, what we want is now the initial conditions for those. So we will start with initial conditions as well. Before starting from there, I want to explain what are what is the dipole approximation, because this is a good point to now do a dipole approximation to simplify the term which we already got for the Rabi frequency. So this is the term we get for Rabi frequency, and if you want to simplify this term, what we want to do is we want to take the E naught term outside the integral. And when can we do that? When can we take the E naught term outside the integral? Because, like I said, so if you want to, if you are not very comfortable with Dirac's notation, then basically what you can understand from this expression is that this is same as psi1 star, then everything in between in the bracket remains the same, ER, E naught, and psi2, the tau, which is the volume. So this actually is, these two statements give exactly same information, but it's just a different notation that we are using right now. And because Dirac's notation is much more elegant, that's why we are using that. But make sure you understand that this expression and this expression give you the exact same information, that we are considering the transition matrix element. So this will give us the coefficient to go from one state to another state. So yeah, like I was saying that we have not made any approximations till now. Now we are going to make the first approximation, which is the dipole approximation. So what does dipole approximation mean? So since we have an atom and the laser is interacting with that atom, so the laser with the incoming light will have a certain frequency. So once you have a certain frequency, you can also determine the certain wavelength for that frequency by c is equal to n lambda. So once we know the frequency, we can find uh, the wavelength for that frequency, where uh, now omega is 2 pi f, and from these two expressions, since we were talking about angular frequencies till now, you can consider the 2 pi factor, and then after considering that 2 pi factor, you can convert to a wavelength. Why are we considering to why are we required to go to wavelength picture again from frequency picture? Is because now we want to understand the spatial extent. So if you have a wave, electric, like a light wave coming in, so then that light wave will have some wavelength, and that wavelength basically helps us imagine what will be the spatial extent for that wave. So if you have a wavelength, what does wavelength mean? Basically any pattern that repeats itself, right? So then if you have a wave like this, which is periodic and doesn't vary in time, then you can consider that it's the same after a periodic interval, right? So if it's the same after a periodic interval, this gives you the wavelength for which it is the same, exact same, and that replicates again and again. So then if this is the wavelength, then we can consider that the atom is stationary and the light is coming and incidenting on the atom. So what we are considering by dipole approximation is basically A naught is the Bohr radius of the atom. So that's the spatial extent of the atom. And lambda gives you the wavelength of the light. So that gives you the spatial extent of the light. So the spatial extent of the light is for a single wavelength, because we have a monochromatic light source. Now we can consider a single wavelength, and what we are considering here is the wavelength of the incident light, which is the spatial extent of your source, is much more than the Bohr radius, basically the spatial extent of the atom. So the atom is like a much smaller part compared to, or much smaller in size compared to the wavelength, like the spatial extent of the laser. So if you consider that, then what you can approximate is the electric field is going to stay the same throughout the atom's spatial extent. So the atom is not going to see any variation in the amplitude of the electric field, because it is like stating, uh, if you consider this picture, then the atom sees only one wavelength, small part, and that will not change the amplitude. It will change the phase, but it will not change the amplitude of the electric field that the atom sees. So the atoms always sees the constant electric field E, but just the direction changes. So what you can approximate here is the dipole approximation, where the wavelength of the incident light is greater than the spatial extent of the atom. So that's why you can take this out of the integral or take this out of the transition matrix element. And what you get is, if you just take this one out, then what remains inside is just ER naught times the position vector of the electric field. And since when we are talking about the position or the direction of electric field, we have to consider now the polarization of light. So the because light can have different polarizations. So if you have a linear polarization, what does that mean? When you have a traveling wave like this, and the polarization is in the x-axis, what does that mean is the polarization is linear and it is changing like this. So if you have a polarization in y-axis, it will be like this. And if you have a polarization in z-axis, that will be like this. So uh, in all three axes, you can have your polarization. You can also have a polarization in an oblique axis, which can be decomposed into a two x and y axis or x and z axis. So you can have linear polarization or you can have circular polarization as well. So you can have different directions of electric field when the light is coming in. So because light is modeled as a changing electric field, we can define the direction of that change as polarization of light. So that's why the polarization of light actually will determine that how the atom as a dipole sees the electric field of the light and what is the direction of that electric field. Because the direction of that electric field will determine how your atom will get polarized. If the electric field is like this, changing in x-axis, then or changing in y-axis, let's say, then your atom, which has a positive core and a negative electron cloud, will get separated like this. It will feel oscillations in y-axis. If your electric field is changing in x-axis, then it will feel oscillations in x-axis. If z-axis, then basically what I'm trying to emphasize is the direction of electric field oscillations matters whenever you're considering this interaction, because the interaction or the variations or the fluctuations in the dipole, the oscillations in the dipole moment will be in the same direction as the electric field. That's why the electric field's direction matter a lot. So we can also neglect anything perpendicular to that, because perpendicular to that it will not have any effect. So that's why the electric field's oscillation direction matters a lot. So all that is to say, if we want to consider that, then we have to take into account how the incident light is polarized. If it is polarized in x-axis, if it is polarized in y-axis or any one axis, or it is polarized in circular uh, way, so right circularly polarized, left circularly polarized, or it is polarized in elliptical polarization. So we can consider all those cases, but those cases are important when you're considering the direction of light. So the dipole approximation basically tells you the direction of light, the direction of electric field matters, but the magnitude of electric field, which is the amplitude, that will stay the same throughout the atom's spatial extent. So that is one approximation that we are making, that since the wavelength of the incident light is much, much greater than the atom's Bohr radius. And you can also compare this. So take any laser, which is like a terahertz laser, find the wavelength for it, which is like take a visible light laser, find a wavelength for it. Wavelength will have to be from 400 to 700 nanometers. So that will be lambda. And then you can consider take any atom and find the Bohr radius, and you can already see that that is 10 to the minus 10, and this is like 10 to the minus 9. Like 400 to 700 nanometers is 10 to the minus 7, I think. So if you consider that, from that at itself, you can consider that lambda is 3 orders of magnitude greater than the Bohr radius. So you can always make this approximation for most cases. So this is the dipole approximation that we are making, that the atom sees exactly same electric field amplitude in all its spatial extent. So if we take that, then to get anything meaningful out of these two expressions, what we are going to do is we are going to consider initial conditions. So initially, if we have a two-level system where all the population is in the ground state, then like basically the electron starts in the ground state. then we have to now ask the question that if we apply light on this system where the system's initial population is completely in the ground state, then what will happen? So if we want to consider that case, then we can consider the coefficient C1 at time t equal to 0. So this is at time t equal to 0. The C1 coefficient is 1. What this gives you is all the population is in the ground state for this is for the two-level system, and there is no population in the excited state. So there is no population in the second state over here. So if that is the case, if we substitute these two in the expressions that we got in the coupled differential equations, so if we directly substitute C2 equal to 0, then this terms goes to 0, and this actually entire RHS goes to 0. And this RHS it goes to 0, then we can consider that C1 dot will be equal to 0. So if the time derivative of C1 is 0, that gives us that C1 is constant. C1 of time is constant with respect to time. And if that is constant with respect to time, then by normalization, we also know that it has to go to 1. So that's why C1 is approximately 1. And if we want to find out the expression for C2, similarly, if you just substitute C1 equal to 0 in this, then you will get expression for C2 as well. So when you get that expression, after getting that expression, if you want to do, so that it is necessary actually to do another approximation, which is the rotating wave approximation. So if you get these two expressions for your system, then this term looks pretty big, right? It looks there looks like there are a lot of terms, and we want to eliminate some terms from it. We want to simplify this term. So initially we started with these expressions. We had these initial conditions. We substituted these initial conditions in these expressions, and we got to these two expressions. So these two are the time uh, dependencies of the coefficients. So the coefficients will evolve. So the coefficients started with 1 and 0, right? And with time, they will evolve, and the time evolution is given by these expressions. And now, if you want to simplify the second expression, then we can simplify it by rotating wave approximation, where you're basically saying that you're staying close. You have applied a laser on your system, which is a two-level system. So that laser's frequency, if it is exactly same as you can choose it to be exactly same, right? So if you have incident the laser very close to resonance, which means that omega is almost equal to omega naught. So if we are at this condition where omega is almost equal to omega naught, then the difference between the two is very small, right? And the addition of the two can be approximated as 2 omega naught. So omega plus omega naught is roughly 2 omega naught, and omega minus omega naught is almost 0. So if that is the case, then we can see that from these two quantities, this expression is true already, because the right hand side is almost 0 and the left hand side is almost uh, like way bigger than the right hand side. So what will happen is you will consider the oscillations. So if the frequency is too high, then you can neglect, because if anything is moving too fast, what that does is in your expression, uh, especially in this expression, if you have a denominator which is very high, this entire term can go to 0. So that's why you can only consider the second term, and you can neglect the first term because this is true. But this approximation now, so this is the second approximation that we are considering, that it is a rotating wave approximation. Um, Forget about the name. The name has a certain significance, but I'm not going to explain that. But rotating wave approximation is basically saying that this condition is true. And if this condition is true, then we can neglect the first term and just get the second term. If we are now focusing on just the second term, then this is 1 minus e to the power I theta, where theta is some phase. This is theta. Now 1 minus e to the power I theta, if we want to simplify, then we can say e to the power I theta can be exactly written as sine cos plus I sine theta. And if we do that, if we simplify, we will get the expression that in terms of just sine, because the cos theta will go to 1 for very small values because cos of 0 is 1. So that's why that 1 and this already existing 1 will cancel out each other. And what expression you will get is like this. So you'll get the expression in terms of sine, and the imaginary part goes away again because you have also taken square. So once you take the square of the coefficient, what you're now getting is the probability of the time evolution. So how does the probability of being in the excited state, or how does the population of the excited state change? So when we started the problem, all the population was in the ground state. So the electron was in the ground state. So what is the probability of getting or exciting the system with a laser that is almost on resonance? So what is the probability? How will the probability change as a function of frequency? So the probability in time depends on frequency, and that profile is actually what you will get whenever you will consider this expression. And this expression actually gives you a nice sine x by x graph, which basically looks like this, which is a sinc function, which has a maxima at the origin, because when you have omega equal to omega naught, this will blow up. So this has the maximum at origin, and then it smoothens out as you go away from the origin, and it goes down. So basically what this is saying is, if your applied frequency is exactly same as the resonance frequency, you will get the maximum interaction between the first and the zeroth level, or the first and the second level. And as you go away from resonance, you will still get interaction, but the interaction will drop. And how the interaction will drop, or what is the function of the frequency, that is given by this expression. And this expression is basically a sinc function. And this function is also what you get, I think, in diffraction of a slit. So you get exact same function as a pattern. And there is a interesting way, there is an interesting intuition why this happens, why there is an expression like this even in diffraction and even here, because it's like we are taking a Fourier transform, and it is very interesting to see that Fourier transform concept is useful even here when we are deriving just light atom interaction, and the profile is exactly same as the diffraction pattern, which is again mentioned also in Foot's book. So this all comes from the Foot's seventh chapter. So here basically we have got an expression for the time dependence of the population of the second excited state of the excited state. So here in our problem, basically we had an atom and we incidented using a light. So now what different cases we can talk about is whether the incident light, is it a weak light, is it a strong laser, is it any different source? So the light can vary from being weak and going to strong. So then for a weaker light, you can imagine that there will be lesser electric field, and basically there will be a small omega. So omega for weak light is much, much small than omega for strong light. And omega is Rabi frequency. So basically, if you have very low Rabi frequency, that means you have very low interaction strength. That means you have very low coupling strength between the two levels. So the two levels, the transitions between the two levels will happen very slowly, or the transitions between two levels will not be very high in magnitude. So this is the language that we are going to now on talk about. The intensity of the laser, or intensity of the incident light. Whenever we want to talk about that, we will talk about Rabi frequencies. So if the Rabi frequency is too high, uh, if the Rabi frequency is high, that means that the laser intensity is high. And if the Rabi frequency is low, then that means the laser intensity is low. So basically, this Rabi frequency, capital Omega, gives you a quantity that you can compare and talk about whenever you want to talk about the interaction strength, or the coupling strength between the light atom interaction. How strong is the interaction? That interaction will depend on two things. One is the dipole characteristics of the atom and the laser's electric field. So the more the strength of the electric field, the Rabi frequency goes up. the more the strength of the dipole interaction, the Rabi frequency goes up. So we will talk about Rabi frequency a lot in this course. And whenever I'm talking about Rabi frequency, you have to understand that I am talking about the interaction strength between these two levels of our atom, because the atom is two levels for us. And again, another thing can be that the interaction is slow. So you have applied for a very short amount of time. You have applied the laser to an atom, which is a two-level system, for a very short amount of time, or you have applied it for a very long amount of time. So you can either have short pulses of lasers basically, or you can have long exposure. So you can interact for a longer amount of time, or you can interact for a very short amount of time. And the physics will be very different when you consider these two different regimes. So these are actually the different regimes that we can talk about by just this derivation. That in the same derivation, if we consider omega to be very small, this capital omega to be very small, then we are talking about a case in the real world where we have interacted with an atom that has a low dipole moment, or we are now talking about a scenario where the incident laser has very low intensity. Now, if you want to talk about a scenario where the incident laser has very high intensity, then in the exact same derivation, we just have to consider the limit where omega is very high. If we consider a limit where omega is very low, we'll go to a different regime. So exactly same derivation, basically, you have to do with different regimes if you want to understand different physical scenarios. And the third regime is where you can talk about what happens when omega naught is same as omega. So if this is the case, then you're on resonance. And if this is not the case, then you're off resonance. So if you're away from the resonant frequency between the transition of the two levels, then it is off resonance. If you're on resonance, then you consider a regime where very different physics works. So depending on which regime you are in, you'll get very different results. And those results are what you are looking for when you're dealing with such experiments, where you can do experiments in all of these regimes in the laboratory. So whenever we are doing research, we first identify that which regime we are in, and then just go to those expressions and use those expressions for our specific problem. So what we are going to consider in the last 10-15 minutes of this lecture. Now I want to just consider one of I want to compare two regimes where we can consider the incoming light to be monochromatic, which is a single frequency. So omega is a single frequency, or we can consider that the incoming light is a combination of different frequencies or has a width of frequencies. And then basically, if we apply a laser which is broadband, which has a lot of frequencies, what will happen? In opposed to if we consider a narrow band laser, which is like a single frequency, what will change? What will be different in terms of physics? So for considering the broadband radiation, actually we have to consider Einstein's A and B coefficients, which is like a beautiful formalism that whenever you have two-level system, so you have just two-level system, there are only three ways possible for the excitation or de-excitation to happen. So you can make the electron go from the ground state to the excited state. So this is one and this is two. And you can make the electron come from the excited state to the ground state, or the electron will come by itself to the ground state by spontaneous emission. So this is stimulated absorption, this is stimulated emission, and this is spontaneous emission. So these are the three processes that can happen. The electron won't go from the ground state to the excited state by itself. So these are only the three processes that can happen in our two-level system, right? So if we incident a laser, because of that laser, the electron can go up, or because of that laser, electron can come down. Those are stimulated absorption and emission. And the third process is spontaneous emission. So this process of electron going up by itself is physically not true. So we will not get this coefficient at all. So we will get a coefficient for spontaneous emission. So spontaneous emission coefficient is A to 1 always, whenever we are considering Einstein's A and B coefficients. So Einstein's A coefficient is basically spontaneous emission, and Einstein's B coefficient is stimulated processes. So stimulated means if we have incidental laser, we are responsible for carrying out that transition. So we are making the electron go from the ground state to excited state or excited state to ground state. We are changing the dynamics of the system because of the perturbation that we have incident. So that is stimulated. And if it happens by itself, if it happens naturally, then that is spontaneous emission. So whenever we are talking about Einstein's A and B coefficients, the A coefficients talk about the spontaneous processes and B coefficients talk about the stimulated processes. And uh, the subscripts give you information about how your journey begins and how your journey ends. So if you're starting from the first state to the second state, you're going up. If you're coming from 2-1, so 1-2 and 2-1 corresponds to going up and down. So that's why B12 and B21 are stimulated absorption emission and spontaneous absorption emission. So it is very nice um, intuitive notation that is given by Einstein. So whenever you have incidented, let's say a light of frequency, specific frequency, that light will have some energy density. So that energy density will be a function of frequency. So if you have multiple frequencies that are incident on light, and then the density is different. What do you mean by that is the amount of light that is there with a specific frequency um, is different compared to some other frequency. So when you have a light coming in which has a broad, let's say a broad um, finite width, then at the center you have the maximum amplitude. So at different frequencies, you can have different electric amplitudes. And what this gives you is basically if you increase the energy density at a specific frequency, you will get more excitation, right? If you have a more powerful laser, you are going to drive the system a lot. So you are going to excite a lot more compared to a weak laser. So uh, when you consider just A and B coefficients of Einstein, you get these expressions. And what these expressions, what this equation is telling us is basically here N2 and N1 are the populations of the ground and excited states. So the N2 is the population of the ground excited state, which is at the second energy level. And N1 is the population in the first energy level. So the change in population of the second energy level is actually same as the change in population of the first energy level. This is the second statement. Why does this make sense? Is because the total population has to remain the same. Because if there is one electron in the system, at the end of everything, at the end of the process, we have to conserve the energy and we have to conserve the particle number. So the total population has to be one. It has to be the same. So the total probabilities all should add up to one, and the populations should exactly be the same. So sorry, this is not zero, this is constant. So which is, let's say, n. So the in total population of the system, if you add up in a population in first energy state and second energy state, they have to be the same number throughout the process. So this second expression makes sense to us, right? And the first expression says that the change in population of the second excited state, which is like this second energy level, change in population of that is proportional to these three terms, which is B12, B21, and A21, which is like these are the three processes that can happen in a two-level system, right? We already talked about this, that these are the only three processes that can happen in two-level system. So that's why the change in population of the excited state has to be dependent on just these three coefficients. Uh, out of which the B coefficients, like we talked about, are coefficients that are there because of the perturbation that we have incidented. So they depend on the laser characteristics that we have applied. So this depends on the laser. So that's why it has a rho omega in it. So that rho omega is the energy density that we have applied externally to carry out that transition. And again, rho omega 2 is there whenever there is a stimulated term basically has an associated energy density term along with it. That is the proportionality constant. So B12 and B21 are the proportionality constants. Whenever you are, and the negative sign and positive sign actually gives you the correct idea that if you are coming down, then you are decreasing the population. That's why there is a negative sign. And if you are coming up, then you are increasing the population. That's why there is a positive sign. So this expression actually intuitively makes a lot of sense that if the population is decaying, which happens in the spontaneous part. So this expression gives you the spontaneous part. So because spontaneous emission, so second term is stimulated emission. This is spontaneous emission. And both emission processes actually decrease the population of the second excited state. So there are two ways the electron can come down from the second level to the first level, either by stimulated emission or by spontaneous emission. So that's why these two processes have negative sign here. That's why the second and third term in this expression gives you comes with a negative sign, and you can see that it is proportional to the population in the second excited state. So N2 is accompanied by this. And whenever you want to go from the first state to the second state, which is stimulated absorption now, that process has because of that process, the population in the second state increases, and that's why it has a positive sign. So that's why first term is positive and all other terms are negative. So that's why this expression, this entire expression together basically gives you the decay, uh, the change in the population of the second excited state. How will that depend on time, or how will it evolve as a function of time? That depends on just Einstein's A and B coefficients, and that Einstein's A and B coefficients are just intuitively make sense because if you have incidented a laser, then stimulated processes all will depend on the energy density of your laser, and the spontaneous process will not have any energy density term because it is happening spontaneously. So that's why it will have just a coefficient with the population. Now the only question that remains is what is the relationship between A and B, right? So how will you relate A and B? So how will you relate the stimulated process with the spontaneous process, or stimulated uh, emission absorption with the spontaneous emission? So how are A and B coefficient related? So Einstein made a clever argument here, saying that A and B coefficients have to be related. And then once you take like Planck's equation in mind, so like this, we already talked about this, that there are three processes that are possible in the two-level system. So when you take Planck's formula for energy density rho of omega, and if you substitute that, there is a nice section in the chapter one, I think chapter one of Foot book, that gives you exactly same information about the Einstein coefficients that I am talking about right now. So Einstein's point was that since the population has to stay constant throughout, then whenever we are not incidenting anything, whenever the electric field or the energy density is zero for the incident laser, if we start with a system where, let's say, some population is in the excited state and there is no laser applied, then this population has to come down, right? Because this is unstable. So this population has to come down by spontaneous emission. And what will be the rate of spontaneous emission is basically you can get directly from this expression by substituting that if you are starting um, from an expression where rho of omega is zero, which basically means you have no laser incident on the system. If you have no laser incident on the system, the first and the second term will just go away. And what that gives you, this expression combined with the second expression directly gives you that this has to be an exponential decay. And the exponential decay is then basically the population in the excited state has to decay exponentially. and has to come down to the first state. And the population decay is also proportional to the population in the second state. So if you started initially basically with more population in the excited state, you will decay faster. If you had less population in the excited state, you will decay slower, which is amazing because if you start with a system where you have all the population in the second state and no population in the ground state, you'll decay very quickly. And the emission profile, like we talked about when we talked about lasers, that the emission profile gives you maximum emission at a specific frequency, which is the resonance frequency. So that's why you get emission from the laser. So this formalism basically of Einstein A and B coefficients, where A coefficients are spontaneous emission and B coefficients are stimulated absorption and emissions. This gives us a formalism to talk about now broadband radiation. If broadband radiation is incident on the atom, then we get, after solving, there is a derivation in foot that you can follow and you can maybe derive it for yourself if you get time. Then the relationship between the A and B coefficients is given by just this simpler expression. Uh, and basically you can, if you know one coefficient, you can get all the other coefficients. And one coefficient is easy to calculate for us because we have literally applied the laser and we know all the properties of the laser. So that's why we can calculate the B coefficients. And from the B coefficients, then we can calculate the A coefficient as well, or vice versa. If we know the atom, we know the A coefficient, and then because A coefficient is essentially the inverse of the lifetime of the state. And if we already know the lifetime of the state that we are talking about, then we can already know the A coefficient. So anyway, I mean, it's this formalism basically gives you a nice flavor to talk about broadband radiation that is incident on the atom. And this is given in chapter 1 of the foot, so you can go through that as well. Um, but the interesting point, so there is one small interesting point that I'll convey in 2 minutes, and then maybe we can conclude and we can do the later part later. So we we reached till a point where we got this expression. We'll start from this expression from the next lecture, and we derived it today. I think hopefully explicitly. I'll send you this note, and you will be able to derive it if you just follow the steps. So you got the coefficients as a function of time, and then later we will look at different regimes where we have either weak laser or a strong laser, or if we have a lower interaction time or larger interaction time, if you are on resonant or off resonant. We will consider all these cases, and we also wanted to talk about monochromatic versus broadband. So for broadband radiation, it is really nice to understand the Einstein's A and B coefficients. So that's why A and B coefficients is what we reviewed today. One interesting point is whenever we are doing experiments, we are always detecting photons, right? So whenever we are incidenting light on an atom, the light scatters off and we get the photon in our detector. So if you now, after discussing all this, after discussing A and B coefficients of Einstein, uh, you can now sort of imagine that all the photons that we collect are spontaneously emitted photons. We cannot collect a emitted photon because if you have a completely stimulated process, let's say you have a laser that is incident on an atom and you have two-level system, then the electron will go from the first level to the second level. It will come down. This process will go on forever if there is no decay of the system. If naturally there is nothing that is making the electron come from second excited state to the ground state, then this process will go on forever. But in the experiments, we don't see that. There has to be energy conservation. There has to be losses of the system. So there is a decay, spontaneous decay that is happening. So whenever this is an interesting point, you can think about it more if you want that. Um, this is the interesting point that we actually my professor told me very recently, that we can only measure a spontaneously emitted photon when we are doing any experiment. We cannot ever detect or we cannot ever measure the stimulated emitted photon because that doesn't exist. That process is a closed process. It's a closed cycle. So when you are driving the transition, it stays in that system and it doesn't get out of the system. Only when you have a spontaneous emission, then you get the photon out of the system, and then you get whatever we call as scattering. So whenever we incident photon on an atom, it scatters off light. And what do you mean by scattering is basically absorbing a photon and then emitting a photon. It is a two-step process. So even if you have a single photon, even if you have a single photon and a single atom, you still have to consider it as a two-step process. It's not a classical scattering process. So you have to consider it as a two-step process. First, the atom will absorb the radiation, so it will absorb the photon, and then it will emit the photon. And what I'm saying here is the emission process. If you are detecting the photon, the emission has to be spontaneous emission. It cannot be stimulated emission. It's a really interesting point if you think about it more. If you want to discuss, you can message me anytime. But yeah, this was an interesting point. So next lecture, I think we will start from the formalism, where we will again consider the monochromatic radiation incident on an atom, where basically you're considering a single frequency laser incident on an atom. We today talked about broadband radiation, and for broadband radiation, there is already Einstein's treatment that you guys can follow. So generally in spectroscopy experiments, we have a single frequency laser and we do everything with the single frequency laser. But there are experiments where people use broadband radiation to just scan the entire frequency space of the atom or the system that we have in hand. So there are both regimes. So there are different regimes that you can talk about. The physics changes a lot depending on the regime that you are in. So it is first really important to identify the regime which you are talking about, and then solve the equations accordingly. Because the initial conditions will vary. Because we always talk about different limits. That's why whenever we are doing approximations, they depend a lot on which regime you are in. So that's why you need to be careful when you are doing a derivation like this, which is light atom interaction derivation is going to be the same, exact same for all the processes. It's just that which regime you are in or what approximations you make, those will change depending on which scenario, physical scenario that you're considering, or which experiment you want to model using theoretical explanations. So, okay, in the next lecture, we will cover Rabi oscillations. We will cover pi and pi over 2 pulses. You're giving that those pulses and you're changing the populations from first state to second state. And we'll also consider block sphere formalism to imagine better what's happening in this two-level system, how to understand the dynamics of the system by just a simple model of a sphere. So I think in today's lecture, what we have covered essentially is Einstein's A and B coefficients, and we have also covered the entire derivation, uh, which helped us go from the coupled differential equations to the solution of the individual coefficients of the two levels, which are time dependent now. So I think if you want to read input, you can read the Einstein A and B coefficient part, and you can also read till this part, till this expression that is given in Foot's book. From next lecture onwards, we will cover the next topics which I have already mentioned in the footbook. And I think in the next lecture we will complete this derivation. So this derivation took 3 lectures, which I expected it will take, because this is not a long derivation. I guess the algebra is pretty simple, but still it's important for us to go through it once so that it sticks in our head. And on each step, actually, the physics is pretty rich. So why are we doing a certain step? Why are we making certain approximation? That I think needs an emphasis. And that's why I'm spending so much time on each simple mathematical step, even though it would be obvious to most of you, I guess. But still, what is the meaning behind that step, and how we can relate this to actual experiments that we do in the lab. So that's why this is taking so much time, but I think it's worth it. And okay, I also wanted to talk about that. So since your semester has started already, so I can talk to Nitin sir, we can figure out some plan as well. But I think I won't be giving any assignments, of course, because it will be difficult for you guys to maintain both classes and this. So I think we can talk about it online on the group, and let me know if I can adjust the lecture timings for you, if any other time would be convenient for you, or do we need to take a short break from the lectures and maybe continue them in your winter break or something? Because yeah, any option is viable actually. And then I don't know whether Nitin sir has joined or not, but maybe yeah, he has not joined. So it's fine. We can talk about this on Telegram group, and we can later decide whether we want to continue this series right now as well, or in the winter break. So we can maybe even change the timings. It's fine. So okay, if anyone has like any questions regarding today's lecture, they can ask, or they can ask me, email me as well. I'm always available. So I think today we can just stop here and we can conclude the lecture unless you have any questions. If not, you can, yeah, you can consider the lecture is done.
Hello.
Hello?
Hello. Yes, sir. As you told about the spontaneous emission, so I have read that means after absorption, the it will be there. It will be in excited state for 10 raised to minus 8 second, and then it's fall down. So means how it exactly work? Like if I already have that in excited state, so how it's come down? Like after 10 raised to minus 8 second, all will come down, or how it happens exactly?
Because the state, even though it is in the excited state, it is not stable. So for us, if it gets a time window, so this is where uncertainty principle comes in. So if you already know about uncertainty principle, what it says is if you have a narrow window of time, so you mentioned like 10 to the minus 8. So if you have 10 to the minus 8 seconds, then by the uncertainty principle, you already know that time and energy are related by uncertainty principle, and then the product of uncertainty in time and uncertainty in energy should be
Hmm.
same as h bar. So h bar you
Yeah, it's
already
good.
know is like 10 to the minus 34 or something.
Hmm.
So if you take that, then if you consider the time window which is 10 to the minus 8, if you transfer it to the other side, then there is an energy that you can exchange with the environment and not break any uncertainty principle, right? So if you take 10 to the minus 8 on the other side, then you still have roughly 10 to the minus 25 uh, energy, and 10 to the minus 25 in EV is like is considerable. So because in EV you have to consider it 10 to the minus 19, so you get like a I think few milli EV or something, like a very small amount of energy.
Hmm.
But that energy you can exchange with the environment, because what is okay? So what is the environment? Environment is basically anything outside the atom and the laser. But since we are doing experiments in real world, we do have some environment, right? And even if we do it in vacuum, even vacuum can be considered as the environment. So now if you know that's the environment, then there is a small window of energy that you can exchange with the environment within that time interval. And then if that energy exchange happens, then it's basically considering like it, if the atom is at an unstable equilibrium like this, it is standing at the top of a hill, then if it gets
Hmm.
any energy push, if it gets any force in any direction, then that force takes it downward. So that's
Okay.
why whenever you have a small time window where the system can exchange energy with the environment, that energy
Hmm.
exchange is sufficient enough to push the system away from the unstable equilibrium. And then that unstable equilibrium, which is the excited state, comes down and goes to the stable equilibrium, which is the ground state. But because the stable equilibrium has a shape like this, which is like a parabola, and even if you push in any direction, you will come back to the same state. But if you have a parabola which is inverted like this, then if you give it a push in any direction, it will fall down. That's why spontaneous emission can take you from the excited state to the ground state, but it cannot take you from the ground state to the excited state because it's very small push that is allowed by the universe. So universe basically allows you to have this like sort of break energy conservation for small amount of time, that you can exchange the energy from system to environment or environment to system. But it's essentially you are not breaking any energy conservation if you are just exchanging with the environment within that time in time energy uncertainty principle. So that's why like that small energy push is sufficient for you to come down from excited state to the ground state. I don't know whether that answers your question or not.
Yeah, yeah, okay, okay. Thank you, sir.